So, what really makes an AI agent smart? I'll give you a hint. It's not just about having the biggest, baddest model. Today, we're going to pull back the curtain on the behind the scenes magic called context engineering. And we're doing it by learning from the team that built the AI agent Manus. Let's get into it. This quote right here is the core philosophy that drove their entire project. Think about it. The choice is pretty simple, right? Are you going to build something that's stuck to one specific model, like a concrete pillar in the sand that's just going to get overwhelmed by the next wave? Or do you build a nimble boat that can actually ride that rising tide of new, more powerful models as they come out? Yeah, the Manus team, they chose to build a boat. And this slide shows you exactly why that choice is such a no-brainer. In the old days of AI, fine-tuning a model meant your feedback loop was measured in weeks. You were basically locked into one piece of tech. But context engineering, it lets you iterate in hours. It's a complete shift in thinking. You're not training from scratch every time. You're building on top of the best new models that come along. All right, so how do they actually pull this off? We're going to break down their wisdom into three core principles. We're talking about engineering for efficiency, for memory, and for resilience. Let's get started. First up, efficiency. Because let's be real, an agent that's absolutely brilliant but is too slow or costs a fortune to run, that's just a cool science project. This is all about making it work in the real world. So at its heart, an agent runs in this really simple loop. And this diagram you're seeing comes right from their paper. It looks at its context, that's everything that's happened so far. It picks an action, gets a result back, and then it adds that new info to the context. Now, here's the crucial part. With every single turn, that context gets bigger and bigger, and that has massive implications for speed and, you guessed it, cost. And that brings us to what they identified as the single most important metric you need to track, the KV cache hit rate. The KV cache is basically the model's short-term memory for all the text it's already processed. Hitting that cache, meaning finding what you need in there instead of reprocessing it, is everything, because it directly controls how fast your agent is and how much it costs to run. And how much does it control it? Well, get this, by a factor of 10. Processing information that's already sitting in the cache versus processing it from scratch has a 10 times cost difference. That's not a small number. That is absolutely huge when you're operating at scale. And this slide just makes that 10x difference painfully real. Using actual pricing from a model like Claude Sonnet, you can see it right there. You're paying 30 cents for a million tokens that are already cached versus $3 for uncached ones. I mean, getting your caching right literally saves you 90% of your cost. It's a game changer. So this all leads to some super simple but critically important rules for how you engineer your context. To keep that cache hit rate sky high, you've got to be disciplined. Keep your prompt prefix stable. A tiny thing like putting a live timestamp at the beginning of your prompt can invalidate the entire cache. Never change the past, only add to it. And make sure your data is always structured the same way. Little mistakes here can silently burn a hole in your wallet. Okay, so we're efficient. Awesome. But now a new problem pops up. What happens when you start giving your agent more and more tools to use? Its range of possible actions just explodes. And paradoxically, giving it all these options can actually make it confused, slow, and, well, dumber. The solution, as you can see here, is surprisingly elegant. Your first instinct might be to just remove the tools the agent doesn't need right now, but that breaks your precious KV cache and it actually confuses the model. The much smarter play is to mask the tools. You leave them in the context, which keeps your cache happy, but you programmatically tell the model, hey, you can't pick these right now. You're guiding the model, not confusing it. So we've made our agent fast and efficient, but what happens when the task is just too long for the model's built-in memory? Well, that brings us right to our second principle, engineering for memory. And here is where we get another huge paradigm shift. You have to stop thinking of the model's context window as its only memory. The real memory, the ultimate context, is the file system. It's basically infinite, it's permanent, and the agent can learn to use it just like we do. This way of thinking lets you use a really clever trick called restorable compression. So the agent can read a massive web page, save it to a file, and then just drop all that text from its active memory, keeping only the file path. The context shrinks, you save a ton of money, but you lose zero information because the agent can always just go and reread the file if it needs to. But okay, even with a perfect external memory system, another very human-like problem creeps in. Over dozens and dozens of steps, the agent can kind of get lost in the middle. it starts to forget what its original goal even was. You've got to keep it focused. The team's solution for this is it's brilliant. They call it recitation. The agent literally creates a to-do list for itself in a file. After it finishes a step, it rewrites the entire list, checking that item off. Now, why does this work? Because by constantly rewriting the list, it's pushing its main goals to the very end of the context. And that's the part the model pays the most attention to. It's an incredibly simple and effective way for the agent to manage its own focus. All right, on to our final principle, resilience. Real-world jobs are messy. Things go wrong. A truly useful agent can't just work when everything's perfect. It has to be tough, and more importantly, it has to learn from its failures. And here, the team shares another one of these powerful, kind of counterintuitive ideas. When an agent messes up, our first instinct is to hide the error, clean up the log and just try again. But if you do that, you're erasing the very evidence the model needs to learn from its mistake. The right move is to leave those wrong turns right there in the context. When the model tries an action and sees the error message that came back, it learns implicitly, okay, that didn't work. It becomes much less likely to make that exact same mistake again. This ability to recover from errors is one of the key signs of a truly intelligent agent. But there's another, much more subtle trap to watch out for. Language models are basically expert mimics. So if an agent does the same action successfully 10 times in a row, it can get stuck in a rut. It'll just keep trying that same action over and over, even when the situation changes. It becomes a victim of its own success, and that makes it brittle. So the solution is to deliberately introduce small, structured variations into the context. Maybe you use slightly different wording, or you change the data format just a little bit. This little bit of controlled randomness is just enough to break that repetitive pattern and force the agent to actually think, which keeps it adaptable and flexible. Okay, let's bring all this home and recap what these principles really mean for the future of building AI. Here are the key lessons from the Manus team's playbook. For efficiency, you have to live and die by your KV cache hit rate. For memory, you've got to think beyond the context window and use clever tricks like recitation. And for resilience, you need to embrace failure as a learning tool and stop your agent from getting stuck in a rut. And ultimately, this is the big takeaway. The next generation of truly capable AI isn't just going to come from bigger models. It's going to be built by the people who master the science of shaping context, one carefully engineered step at a time. And that leaves us with a really fascinating question to chew on. If an agent gets really, really good at using external memory, does it still need the massive, all-seeing attention mechanism of a transformer? Could this lead to a whole new class of models, maybe agentic state space models, that are just way more memory efficient by design? That could be the next huge leap in AI. It's a pretty wild thought. I really hope this explainer on context engineering was useful for you. For more deep dives into the papers and methods that are shaping the future of AI, make sure you subscribe to VibeDoc on YouTube. Thanks so much for watching.